Hello everyone, welcome to the course Design and Analysis of Algorithms. Today we will be looking at substitution method, that is one of the methods to solve the recurrence equations. The substitution method comprises of two steps. The first step is to guess the form of the solution. The second step, we use mathematical induction to prove that the guessed solution works. Proof by mathematical induction consists of two steps. The first step is the base step, in which we prove that the guess is true for the initial value or the boundary condition. And the second step, which is the inductive step, we prove that if the guess is true for some value of k which is less than n, then it also implies that it is going to be true for the value of n. The inductive hypothesis is applied to smaller values, similar like recursive calls bring us closer to the base case. The substitution method is a powerful method to establish lower or upper bound on a recurrence. It is applied in cases when it is easy to guess the form of the solution. Here we are given a recurrence equation of merge sort. So let's see how we can solve this recurrence using substitution method. In the first step, we will make a guess on the upper bound of the solution. In this case, we will assume n log n to be the upper bound on merge sort. So we'll have to solve this asymptotic notation of big O, and we have to find some constant c and some value of n naught, after which for all values of n, the condition t of n less than equal to c n log n is true. Our hypothesis is that for any value of k less than n, the condition t of k less than equal to c k log k should be true. So in this case, we will use k is equal to n by 2, which is less than n. First, we will solve the induction step, and then we will go to the base step. In the inductive step, we will substitute our hypothesis in the recurrence equation and prove that if it's true for value of k, then it should also be true for the value of n. So in our recurrence equation, we need to find out t of n by 2. So we will plug in n by 2 in our hypothesis, and whatever result we get, we plug that in our recurrence equation here. So now let's solve this equation. So this 2 will cancel out with this 2, and we are left with c n log n by 2 plus n. We can further expand log n by 2, and we get the equation cn log n minus cn log 2 plus n. Here Lg is log base 2, so log base 2 of 2 is 1. So finally we will get cn log n minus cn plus n. We want to prove that the result we got from the hypothesis in the inductive step should be less than or equal to the guessed solution, which is n log n. This would be true when the minus c n plus n term in the hypothesis result is less than or equal to 0. If we solve for that, if c is greater or equal to 1, then this condition is satisfied. Hence, our guess on the upper bound solution of merge sort, which is n log n, is correct. Now, let us look at the base case. Base case occurs, as we can see from the recurrence equation, when n is equal to 1. So if we plug n equal to 1 into our hypothesis, we will get t of 1 equal to 0, which is impossible as t of 1 is equal to 1. We only want to show that our guess is correct for sufficiently large value of n. So there exists an n naught, after which for all values of n, our guess should be true. So we can try any value of n greater than 1. Since in the recurrence equation we have a floor of n by 2, so if we plug in 2 and 3 here, this floor will lead us to t of 1. Hence, for this type of recurrence equation, we must choose both 2 and 3 for our base case. So we want to satisfy both of these conditions simultaneously. To compute the value of c, let's solve these equations together. So for t of 2, our value of c is greater or equal to 2, and when t is 3, we use n equal to 3, our value of c is greater than, approximately greater than 1. To satisfy both of these equations, we will pick the value c is equal to 2, which is greater out of the 2. So we prove that t of n is less than c n log n, which is our guess, when the value of c is equal to 2 and n not equal to 2. So we can say that our guess is correct and n log n is the upper bound of merge sort. So let's see what happens if we choose the wrong guess solution for our recurrence equation. Let's choose n as our guess solution, and so our hypothesis will be t of k less than c k for all values of k less than n. We will use k is equal to n by 2. So let's plug in the hypothesis in our recurrence equation, and if we solve this inequality, we get c plus 1 times n, which is not equal to or less, which is greater than c of n, but it should be less than c of n, which is our actual guess solution. So the above inequality does not hold. Hence we can say that big O of n is not the upper bound of merge sort. We can also prove the lower bound of merge sort using substitution method. If we can show that t of n is greater or equal to c n log n. We plug in the hypothesis in our recurrence equation and we solve. Here we can see that the term minus c minus 1 plus n. So there is a positive term being subtracted from c n log n. Because c cannot be less than 0, so this will always be a positive term if c is greater or equal to 1. Hence, this term will always be less than c n log n. Hence, our induction step is satisfied. We also want to satisfy the boundary condition, which is the base case, that is t of 2. If we solve that, we get c is greater or equal to 2. So in other words, it is enough if c is greater or equal to 2. By the requirement c is greater or equal to 1, for the induction step, we choose c equal to 1. Since we are solving for the lower bound, we will choose the smaller value of c out of the 2. So we can prove both the induction step as well as the base step. To prove the lower bound, we will have to prove that t of n is strictly increasing. Assuming for all values of k less than equal to n, it holds that t of k is greater than t of k minus 1. So we want to show that t of n plus 1 is also greater than t of n. For the base case, it is satisfied since t of 1 is 1, which is less than t of 2, which is 4. So we substitute our hypothesis in the recurrence equation. the n plus 1 over 2 floor will become n by 2. So we'll get the equation 2t of n by 2 plus n plus 1. So if we note here that 2t n by 2 plus n is our recurrence equation, which is equal to t of n. So we replace that by t of n here. Hence, we can say that t of n plus 1 is greater than t of n because it's equal to tn plus 1, and a positive constant is being added to t of n. Hence, it will always be greater than t of n. So we prove that t of n is greater than equal to c n log n, with c is equal to 1 and n not equal to 2. So we prove that the lower bound of merge sort is n log n. So now let's have a look at a different problem. The recurrence equation of worst case scenario of quicksort is given. To solve it through substitution method, the first step should be to make a guess. In this case, we make a guess solution of n square. Our hypothesis will be t of k less than equal to ck square for all values of k less than n. In this case, we will choose k as n minus 1. So in the inductive step, let us plug in the hypothesis in our recurrence equation and solve. So we get cn square minus 2cn plus c plus n. Recall that c and n should always be positive. So there is a theorem that states that a sum of two positive numbers is always less than the product of those two numbers. So in this case, we can see that here is the sum of two positive numbers c and n, and here is the product times 2. Since the product is the negative term and the sum are the positive term, so this term will always be small. These three terms here will always make the whole thing less than cn square when c is greater or equal to 1. That proves our inductive step. So now in the base step, if we plug in 1, we will have t of 1 less than or equal to c. So if we choose c equal to 1, we prove that t of n is less than cn square with c equal to 1 and n not equal to 1. Hence, n square is the upper bound of worst case scenario of quicksort. Now the question arises, how do we actually make a good guess? Unfortunately, there is no general way to guess the correct solution to recurrences. Guessing a solution takes experience and occasionally creativity. There are some heuristics that can help us make good guesses. For example, recursion tree method that we will study in the next lecture. If a recurrence is similar to the one we have seen before, then guessing a similar solution is reasonable. For example, consider the following recurrence. T of n is equal to 2t n by 2 plus 17 plus n. It's similar to merge sort, so we can make a calculated guess of the solution as n log n. Another way to make a good guess is to prove the loose upper and lower bounds on the recurrence and then reduce the range of uncertainty. For example, start with and prove the initial lower bound of t of n is omega of n for the recurrence, and then start with and prove the initial upper bound of t of n is big O of n square. Then gradually lower the upper bound and raise the lower bound until convergence to the correct asymptotically tight solution, that in this case is n log n. Sometimes the correct guess at an asymptotic bound on the solution of a recurrence doesn't work. This can be solved by revising the guess and subtracting a lower order term in the guess, as we will see in the example in the next slide. Let's have a look at this interesting recurrence relation. Our guess on the upper bound in this case is n. Our hypothesis is t of k is less than or equal to ck for all values of k less than n. We will use k is equal to n over 2. Let's plug in the hypothesis in our recurrence and solve it. And we get Cn plus 1, which does not imply that T of n is less than C of n, because there is a positive constant being added to C of n, which makes it greater than the actual C of n. We need to show the exact form. Although this is order of n, but by induction step we cannot prove this. To overcome this hurdle, we revise our guess, say T of n is big O of n square. However, our original guess was correct. There were just one additive term that was creating an issue. So sometimes it is easier to prove something stronger. So we will keep our guess as n, but we will subtract a lower order term from the guess, b in this case, which is a constant. Our hypothesis will be T of k is less than or equal to ck minus b for all values of k less than n. And we will use k equal to n by 2, which is less than n. So plug in the hypothesis in our recurrence and solve it. So we come to Cn minus 2b plus 1, which is less than or equal to Cn minus b if minus b plus 1 is less than or equal to 0, when b is greater or equal to 1. Let's move on to the base step and plug in n equal to 1 in the hypothesis, and we will get b is less than or equal to c. So we prove that T of n is less than or equal to Cn minus b with c equal to 2, b equal to 1 and n not equal to 1. So for this problem, n is the tighter bound solution. Now let's have a look at this very interesting recurrence relation. It looks quite complex, but we can simplify this recurrence with a change of variables. Let's rename log n as m. Then we have t of 2 to the power of m equal to 2t 2 to the power of m by 2 plus m. So we have m equal to log n here. So in this case n will be 2 to the power of m. Now let's define t of 2m 2 to the power of m as sm, which is a new function. So we get the following equation after replacement or substituting in this equation. S of m is equal to 2s m by 2 plus m. Does this recurrence look familiar? Yes, it looks exactly the same as merge sort. In merge sort we have n and t here, so it's exactly the same. So for merge sort the complexity was n log n, so in this case the complexity will be m log m. So finally if we substitute the value of m, which is log n, in m log m, so final answer we will get is log n times log of log n. I hope you have enjoyed today's lecture. Here are some practice questions to get you familiar with the substitution method. That is it for today. Thank you.